welcome to the Hanover Fair at the group exhibit Hydrogen Fuel Cells and Batteries. It's a pleasure for me to see safe, low-cost hydrogen storage presented by Stephen Bennington, CEO of Cella Energy. Mr. Bennington.
Thank you.
Hi.
Nice to meet you.
You're welcome.
Okay. So I'm from a company called Cella Energy. We make this stuff. It doesn't look very exciting, but it's a hydrogen storage material. It's like a plastic. So you can mold it and you can shape it. You can do what you like with it in terms of making it into different forms. But when you heat it up to 100 degrees centigrade, it gives out hydrogen. It gives out a lot of hydrogen. So to give you an idea, 1 gram of our material gives out about 1 liter of hydrogen. And it's safe. You can hold it in your hand. It's mildly toxic, so it's less toxic than, for example, gasoline. So it's something that you can store and transport safely. And at room temperature, it's stable. So room temperature, it doesn't go anywhere. You can leave it on a shelf, and you can leave it on a shelf for years, and it will not lose its energy. So it's a kind of a very convenient and safe and simple way of storing hydrogen. Now this rather busy slide then talks about how we might use that. So it's we've been developing the material now for quite a number of years, but you can't just sell it on its own. So we've been trying to set up an entire value chain so that we can sell the material in different markets. So we've been developing with our engineering partners now, let me just get this right, is that the one? I don't know. Our engineering partners here, 3 different size systems. So a small scale system that you could use in things like unmanned aerial vehicles, and then on to other more price sensitive markets. Then a medium scale system that we're developing for electric vehicle range extenders. And then ultimately sort of large scale systems that you can use for vehicles, the kind of things that people get terribly excited about. And suppose you are aiming for this final zero emissions vehicle kind of idea. To give you an idea of scale, 10 kilograms of our material will take you 100 kilometers. So it's kind of practical. You can put that in the back of your vehicle, and it could give you the kind of range that you might expect. Let's go through some of these things one by one then. So the first market that we see as being tractable is the unmanned aerial vehicle market. And the reason for that is that they are desperate for power. So I don't know if you've seen some of the small unmanned aerial vehicles around, but they certainly some of the ones with 4 rotors, their flight times are something like 12 minutes. And that's certainly not enough. If you want to sort of survey a turbine blade or survey your oil rig, 12 minutes with a lithium-ion battery is nowhere near sufficient for you to be able to do your job. We can make a system which has 3 times that energy per kilogram and give you the range that you need to be able to complete the mission that you want to complete. The way it works is extremely simple. There are no moving parts. You have a printed circuit board at the bottom. On top of that, you place your pellets of our material. It's all set into a foam matrix for insulation. And because the hydrogen comes out, whatever pressure you like, really, but because we can, in this case, we've designed it to come out at very low pressures, you can form your container into any shape you like. And just to show off in this case, we've designed it to fit inside the wing section of a small air environment Raven. The market is potentially enormous. So the Federal Aviation Authority in the United States is currently deregulating, which means that although it's largely a military market at the moment, by 2015, they will be opening up other civilian uses of unmanned aerial vehicles. The big one is meant to be agriculture, so looking at crops just to see if they're ripe and ready for harvest. But early markets are likely to be things like marine, Coast Guard, fisheries, those kinds of things. The ones we're working with are also interested in surveying things like transmission lines. So at the moment in the UK, they have to survey all the transmission lines every few weeks, and they use a helicopter with an infrared camera. They would much rather be able to do that with an unmanned aerial vehicle. It would so much cheaper. So Those are the kind of applications we're talking about. It is a billion-dollar market at the very least. This one here is for the far distant future. So this is delivering of pharmaceuticals. This is done by DHL in Germany, in Bonn, right now. So they're using it to deliver across the river in Bonn. So we've actually done it now. So we ran this in January. We made our printed circuit board there, and we packed it full of our material, and it worked. So this initial test was a test of the control systems and a complete fuel cell test. It operated beautifully. We're now just making it lightweight and ready to fly. So we're aiming to flying that next month in readiness for the air shows in Florida and in Farnborough later in the year. So that's now a working system, and we have a number of mostly military partners who are looking to develop that a little bit further. We also got a grant. One of the earliest markets that we understand that the Federal Aviation Authority is going to release is marine, because of course there you can't spy on anybody and you can't crash into anything, well, not much. So this will become one of the earliest markets for civilian unmanned aerial vehicles. And for areas like Florida, where we also have an office, Coast Guards are very keen to be able to have eyes in the sky to keep people coming out from Cuba and catching them. So there's a big market there for us. This is the next system. This is a 1 kilowatt system. It's a proof of concept system. And in that case, we package our material into cartridges, this kind of size or bigger. Because our material is a plastic, we can push it in and make it into any shape we like. We can extrude it into rods. In this case, we extrude it in large diameter rods and slide it into a cartridge. We use this, well, think of a gun. Think of something like a Gatling gun, where you have a system which pushes it into a barrel. That barrel is kept hot. The hydrogen comes out in 2 to 3 minutes. You then have a piston system which takes it out and drops it back into a magazine. And when you want to refuel, all you do is you lift the magazine out and you put another one in. So you can refuel in seconds. So this system, I said, it's a bit large and clumsy. You can see it on our stand on C33. But it's a test system. It's one where we can change the temperatures, we can do different heating regimes, and we can work with it. We have funding now to take that on and scale it up to 5 kilowatts. We have 2 projects, in fact. One to put it into a small microcab vehicle as a range extender, and that vehicle would give it an extra 120 miles of range, which we're hoping to get done early next year. And the other project is hydrogen diesel co-combustion. So in that case, what you do is you feed a small amount of hydrogen, 3 to 5% by energy, into a diesel engine through the air intakes, and it changes the combustion chemistry in your engine, and it cleans up the particulate emissions. So we're aiming to try and use that initially in the London low emission zones. I don't know if you realize how expensive it can be. If you have a diesel engine in London which is not Euro 3 compliant, or even, sorry, I think it's Euro 4 compliant now, then you're fined. For a small vehicle, it costs you £100 every day. For a large vehicle, it's £200 every day. It's extremely expensive. So most operators take out their old vehicles and use them somewhere else and try and just buy brand new vehicles for use in London. But some people can't. The average age of a bus in London is 11.4 years. The average age of a London taxi is 15 years. At the moment, there are some exemptions, but they won't last. So they need a system that they can fit in the back of their vehicle, something like our cartridge system, that we can feed into the air intakes, clean up their engines, and make them Euro 6 compliant. So that's, we think, going to be an interesting market for us in the not too distant future. The first markets, of course, here, these are premium. The unmanned aerial vehicle people are willing to pay quite a large amount of money because they simply cannot do what they need to do currently. So we believe that these markets are going to be the ones where we will sell first, but it's a relatively small market. It's a market which will be selling for us the order of tons of material a year, and we would like to scale that up to get it to thousands of tons and beyond. So this is only a stepping stone. This will drive the cost of the material down to the point where the next markets, like the the diesel emissions markets will come into play, and that will scale it up further and drive the costs down even more. The same system has also been picked up, and this was a surprise to us, by the aerospace markets. So we now have aerospace collaborators who want to take the cartridge system and put it into commercial airliners. The reason for that, again, it's driven by regulation. So the Federal Aviation Authority in the United States is deregulating the use of fuel cells in commercial airliners soon. They reckon as soon as 2015. So every aerospace company in the world has a large fuel cell project currently running, and they are worried about compressed gas. They're worried partly for safety, but mostly for logistics purposes. And so they are interested in looking at alternatives. And so we have a number of contracts now to develop systems, test systems, that they can trial in the aerospace market. The kind of things they're talking about using it for example, are powering galleys, kitchens on aircraft. So you've seen those trolleys that people push around in aircraft for full of food. What they want to do is use that to package our cartridges. That will then be plugged into the aircraft galley, and then they would use a combined heat and power. So they would take the heat from the fuel cell to go and heat up the coffee, for example, or the ovens, and they would use the electrical supply to power the galley and the toilet, which is usually adjacent to the galley. The reason they want to do that is in a combined heat and power solution, it saves weight. So the takeoff weight of the aircraft can be lower. It's more efficient than taking energy from the main engines, which is what they do now. And they can strip out all of the heavy cabling, power cabling that's in the aircraft, which also saves takeoff weight. So it's not a green application. Neither of these two are green applications. They're applications that are entirely about performance. The other thing they like is logistics. It's very, very easy to package these and just transport them to every airport in the world and then just wheel them onto aircraft. The aircraft industry are used to that kind of logistics. They do it for food and other things already. So it seems to work for them. Now, this is the big one, and it gets everyone excited, but it's a long way off. We all know that fuel cell vehicles are now just about to come out. So you know the Toyota vehicle was exhibited at the Toyota show late last year. The Honda Clarity has been around for a while now, and their new vehicle is coming out soon. Pretty much all the OEMs are working in collaboration on fuel cell vehicles, which is great. But this is what they're currently using, of course. They're using compressed gas solutions. So these are carbon fiber wrapped high-pressure tanks, and they are beautiful. They're really well-designed pieces of engineering, and they are bulletproof, literally so, because I think most of them are made in America. A lot of them are made in America. But the problem is the compressor, of course. The compressors, again, beautiful pieces of engineering, but they are expensive, difficult to maintain, and you need a lot of them. And so that, at the moment, is the barrier to market for the use of hydrogen and hydrogen vehicles. It's the cost of those compressors and setting up the infrastructural chain you need to run those vehicles. So obviously we could do it potentially in a different way. So our idea now is to form our material into small pellets. I haven't got any with me, I'm afraid. But you just make them, you extrude them in rods, chop them up, you coat them in another plastic to protect them and act as a filter. And those pellets are like a fluid. So if you can imagine a swimming pool full of those little M&M sweets, you can imagine you could do backstroke in that. It's a liquid, it's a fluid, and you can pump that around. And the technology you need to pump that around is incredibly cheap and simple. It's a vacuum cleaner. So I don't know if you're familiar with the British company Dyson, but that kind of technology is all you need to be able to move this material around. And we have a demonstration on our stand you can see. So the idea would be that you could transport the pellets by tanker. So you could put it in something which is very similar to the tankers that gasoline is transported in. They're actually more like grain. I don't know if you've seen these tankers they transport grain in. It's that kind of thing. And that then goes to the filling stations. The filling stations are almost the same, except that this time they have to store the used pellets. And the pumps that are there are cheap Dyson vacuum cleaners, effectively. And the only real difference is that, for as far as the consumer is concerned, is that we have to have two nozzles. One to take the old used pellets out, and one to put the new pellets back in. But apart from that, it's much the same. So inside the vehicle, you have a very simple system. You can have a tank which holds your pellets, and that tank can be pretty much any shape you like, not completely any shape you like, but you can mold it and make it simple, make it conform to the shape of the vehicle, and it can be made of plastic. There's no pressure, there's no high temperatures, so it can be very lightweight. A simple pump then pumps the pellets into a hot cell. That hot cell is maintained at 100 degrees Celsius. The hydrogen's driven out to a buffer volume where it's held until it is needed by the fuel cell. That system is cheap and simple, largely made out of simple, cheap components and a lot of plastic. And it can be made so that its performance, well, I'll show you the performance, is very similar to the compressed gas. So this calculation is done for the complete chain. So the diesel engine at the top there, that contains an engine plus the transmission, so it's the power to the wheels. The battery electric is, of course, the battery plus the motors. And then for the hydrogen systems, that contains the fuel cell and the motor. So it's a complete system we're calculating here. And ours, given the inaccuracies of our knowledge at the moment, is almost exactly the same as the compressed gas solution, but without the high pressures and without the cost of the logistics. So we think it's a viable system, and as fuel cells improve and as our system improves and our materials improve over time, we think that we'll never quite get as good as diesel, but it's approaching close enough for it to be viable. And so the calculation here is for a small vehicle, 50 kilowatts, and we've given it a range of 550 kilometers, which is a real struggle for the battery electric vehicle, but quite possible for the hydrogen fuel cell vehicles, easily possible. Our material, though, is not one that you can just expose to hydrogen and it will soak up hydrogen. It's a chemical hydride. So it's a little bit more complicated than that. It has to go back to a chemical plant where it's dissolved in a solvent, and it goes through a chemical process and you can regenerate it. So we have to be closely linked to the chemical industry or a petrochemical industry so that process can be done. And so that means that you have a full cycle. So you have to collect the material. So the tankers that are delivering the beads to the filling stations have to take the beads back to the chemical plant where they're regenerated, and then that cycle continues. But we think that's ultimately possible. At the moment, that regeneration process is done in our labs and our collaborators, which is the Los Alamos National Laboratory in the States. So we have it working as a laboratory process, and we have an industrial collaborator, a chemical company, which is now trying to put that into the pilot plant scale. For the early markets, like the unmanned aerial vehicles, we don't care, we'll just throw it away. But for the larger markets, we have to have it in place. So for the future, we need to get that working. Cost is absolutely important. When we talk to the car industries, they only ask me two questions, ultimately, and that is, how much does it cost? And the other one is, can you help us meet the legislative targets that the government's imposing on me? So this is our cost, so we are more expensive than compressed gas. And this is a full life cycle cost. And we're talking about here investing in new plant so that you can make it the material at large scale, and then getting the regeneration working, which drives the cost down to low levels. And ultimately it goes much lower than that. But by 2025, that's what we and our chemical supply companies estimate it will cost, compared to compressed gas hydrogen at the filling station. So that you might think is a problem. But of course, I'm not expecting you to read this, but I'm just showing the kind of calculation that we do. Total cost of ownership is the most important thing you need to know. So in that case, you have to take into account the vehicle purchase price, the maintenance cost, its fuel cost, and importantly, the infrastructural costs. Because our infrastructural costs are much lower than for the compressed gas solution, In this case, by 2030, we believe that we'll be beating battery electric vehicles by some considerable margin, and would be equivalent to the compressed gas solutions, and sort of approaching the costs of diesel and gasoline, but not beating it. But this calculation is done assuming no subsidy at all. All right. So if the existing subsidies for green power continue, then we should be approaching these figures by 2025, not 2030. So I'm getting to the end. The last thing that the car companies always ask us is, what is the CO2 emissions? Because of all the car companies are having to, well, the European ones anyway, conform to a fleet average CO2 emissions regulations. And so it's really important that the CO2 emissions are low. And the problem with all green power is that they ultimately come from electricity. So if your battery electric vehicles, of course, if they're using coal-fired power stations, they're not at all green. So we've had to do what they do, which is cheat slightly, and assume that sometime in the future, all your power is coming from wind farms or solar panels. And if we do that, then we can show that our system, going through its recycling process, can cut your CO2 emissions dramatically, and so the car companies can hit their regulation targets. So last slide, just to show where we are as a company. We've only been around since 2011, so we haven't been around long, and we're a materials company primarily, although now we do have a lot of partners who are engineering firms. So we have our material ready. We've done our proof of concept devices. That was very recent. That was all at the beginning of this year. They are now complete. We're now moving into the regime of doing commercial prototypes with our commercial partners, aiming to get into field trials. For the unmanned aerial vehicle, we'd like to be doing that by the end of this year, and for the larger scale systems, probably sometime next year. But that's where we are at the moment. Thank you very much.
Yes. Mr. Bennington.
Yes.
Would you accept some questions from the audience?
Of course.
Just looking at you, do you have some questions for Mr. Bennington after his presentation now? Just one or two? Something in mind? I get to you with the microphone. Just thinking, right?
I have a question about what you show on the filling station for the automobile. You're talking about something like MMM and slices and pellets. Why not just make a pseudo standard size length, width, height as one of your storage medium and directly replace, instead of still relying on tons or numbers of these pallets inside and went through some sort of generation process to get hydrogen out?
That's a good question, and it's for two reasons. The first reason is that, of course, you have to take the stuff out. So, it has to go for recycling, and it's much easier if it's a fluid. So, what's the biggest thing you can lift? Well, for regulation in the EU, it's something like 20 kilograms. So the biggest battery pack or system that you could just lift in or put into a vehicle or into anything is around 20 kilograms. So if you're filling the back of your car with fuel at the moment, you're probably putting in somewhere between 40 and 50 kilograms of gasoline. For our material, you'll need more. You'll need somewhere between 60 and 70 kilograms of material. You can't lift that. But if you're filling it with a fuel pump, you don't notice. It's just easy. So it's mostly for convenience and for the ability to transport it around. But there is one more technical reason. Our material it undergoes a chemical reaction. So when you heat it up, then that chemical reaction also generates a little bit of heat. So for these cartridges, we would heat just here, and then that chemical reaction would heat the rest of the material, and it would progress through the whole of the material. So if you had a big tank of it in the back of your car, and you heated it to 120 degrees C, the whole thing would go, which is why we do it in batches. All right. So in the small unmanned aerial vehicle, it's small pellets, one by one. Here it's cartridges, one by one. And then in the large-scale applications, we pump half a kilogram at a time, or maybe less, into the hot cell, heat that up, drive all the hydrogen out, and then take the beads out and store them. So you have to do it separately. You can't do it all in one go.
And when you convert when you extract the hydrogen out of your material, is that a quick on-off?
It takes, it starts immediately if you heat it right, and you can control it. So on a cartridge this size, if we heat the complete length all at once, then all the hydrogen comes out in a minute or under a minute. We find that a little difficult to control. That means you've got a huge amount of hydrogen that you have to store and then the fuel cell uses. So what we tend to do is heat it more slowly. We tend to sort of heat one end and allow the reaction to move through it slowly. And we control the temperature so that the hydrogen comes out at the rate we are comfortable using. So we on this kind of size, we would try and aim to get the hydrogen out in about 3 minutes. But we can do it faster, but we would try and aim for 3 minutes normally for the 1 kilowatt system.
Thank you very much. I see you got further information to deliver, because there are not only this person interested in. Several faces are looking also very glad about, fine idea. So where can we meet you right now?
We're on stand C33, so just over there. You come and see us. We're more than happy to talk.
This was Safe Low-Cost Hydrogen Storage by Stephen Bennington, CEO of Cella Energy. I have to thank you very much.
Thank you.
And
It's been
see
a
you
pleasure.
then at C34.
33.
33, okay. Thank you very
C33.
much. Now, the next is about non-flow through air-independent fuel cells for advanced aerospace applications by William Smith, President of Infinity Fuel Cells and Hydrogen. We'll start in 3 minutes.